All right, good morning, everybody. Last week we talked about logarithmic functions, and remember the big idea behind a logarithmic function is the fact that the answer represents a power. For today, then, we're going to talk about the graphs of logarithmic functions. So here we go. The parent function, don't forget, for a logarithm is y equals the log some base b of x. Now, it says a logarithmic function is the inverse of an exponential function. Using your graphing calculator, sketch the following two graphs. Well, with the calculator, basically saying use Desmos to check them out. But remember, we've already drawn these before. This is what we call an exponential here. So we have an exponential function. This is our logarithm. How do we know the difference? This one literally says the word log. And remember, this is a base 10 logarithm. So we have already drawn an exponential function. This is the parent function. And remember what we said. When we draw an exponential function, we always go to the same 3 points, -1, 0, 1. What we mentioned in class was if I give this a power of -1, then all I'm doing is a reciprocal. So it's 1 over 10. Plug in a 0, and of course our answer is always a 1. Anything to the power of 0 is 1. And if I give it a power of 1, then we get an answer of just 10. And so an exponential function, we said, has a horizontal asymptote right through x equals 0. It always hits the point, right? In this case, 0, 1. So it always hits 0, 1. And then the next point it hits, now this one I'm just going to have to draw it out and say that's the number 10 up there, just because the number's too big. But then in this case, it hits the number 110. Now the other one is very small, so at -1, we would be just over the line. And so here we go. It is like a plane taking off on us here because it is increasing, right? This is exponential growth because of that 10. So again, these are things that we've already done before. Now, this idea of inverse. Remember, an inverse is something that undoes a function. So for instance, if I say, what's the inverse of adding? Well, in subtraction, because that's how you get rid of adding. What's the inverse of division? Well, that's multiplication. That's how we get rid of it. And so what we're going to be learning today is when it comes to inverses, remember, this is the idea where a log and an exponential kind of cancel each other out. And one of the things that we always do when we mention the word inverse is we switch the x and the y. So if we already know how to draw this one, right? We know how to draw exponentials. If a logarithm is just an inverse of that, well, then all I have to do is switch my x's and my y's. So we would say x, y. We said we're going to switch our x's and our y's, so then it's 1 over 10, and then it's -1. Switch my x and my y, so it's 1, 0. Switch my x and my y, and so then it's 10, 1. And now looking at it carefully, well, let's see, let's try to draw this thing. Oh, almost forgot. Remember, this thing has a horizontal asymptote, and the equation is y is equal to 0. But if we're switching our x's and our y's, remember, everything is changing. Then this is not going to say y equals 0. The new asymptote is going to say x equals 0. And if I draw x equals 0, well, now we have what we call a vertical asymptote. So you see, there's the beginning of the inverse. If this says y equals 0, well, then here it says x equals 0 is what we call our vertical asymptote. So there is a major difference. Look at that. We had a horizontal, now we have a vertical. And then, of course, we have the points, or these numbers. We have 0, 1. So before, so now it's 1, 0. So here's 1, 0. And then the other number is now 10, 1. So 10 and then 1 would be here. Remember, in this case, yes, it's a base 10. We wouldn't say growth or decay, but I can say that my graph is increasing because of the 10. And then it's 1/10 and then -1. So look at that. That's me getting closer to the asymptote, just like we used to over here. But now it looks like this. Remember, the inverse is the idea of switching an x and a y. So if you know how to draw an exponential, you can very easily use those points to help you draw a logarithm. Now, a logarithm, notice, there's no negative values. I'm being cut off right at 0 and being told you are not allowed to plug any negatives here. So that is one of the big notes about a logarithm. We are not allowed to take logs of negative numbers based on what we're seeing here. So in general, let's see a couple points that matter. If this one was always 0, 1, well, then I'm always going to have 1, 0. And then this was just my base, and then my answer is 1. So this fraction is always kind of a weird one. So I want to concentrate on these points. If I can get the asymptote and these 2 points going for any problem, then we're going to be good there. It'll be a lot easier if we do that. So in a logarithm, right, when you have the parent function, there's 2 points you're always going to work with for the parent function. It's going to be 1, 0. That's automatic. And then whatever the base is, 1. These are the 2 points. We see them right here. Look, it's always going to be 1, 0. And then whatever the base is with the 1. The other one we could do is also the 1 over b. My answer is -1. So we can keep using that one if we want. But then the other big thing is we have a vertical asymptote. And that vertical asymptote is x equals 0, aka the y-axis. So for a parent function, these are the 3 things I need to remember. 1, 0, b1, those are 2 points, but we have a vertical asymptote. Remember, we need to draw it out. So we are going to have an increase and a decrease. We don't tend to call it growth and decay, although you can still technically use those words. All right, so because you can only graph base 10 logarithms on your calculator, we'll need to use the inverse exponential function. All right, we already did the graph. We don't need that part there. So let's try this out. Let's see how it goes. All right, so I'm going to try to keep it all there so that I can see what all parent functions should go with. My vertical asymptote. And notice there's no extra number here. There's no up, down, left, right. This right here just has a base and then the x. So this is the parent function. I do see a number 2, and that's greater than 1, so it will be an increase. All right, so let's see what this thing looks like. All right, so we're going to try a couple points. And remember, we are going to go with our usual for a parent function. It is automatically 1, 0, and then base. Well, don't forget, your base was a 2. That's why it's an increase. So there's my base. And then a 1. And like I said, if you needed a third point, you could go 1 over base and then -1 on this side. So you could do 1 over base and then -1. A little bit tougher to draw, of course, but here we go. Look, we're ready to draw it. I have everything I need. I'm not moving up, down, left, right. So here comes the asymptote. We draw that in. So my vertical asymptote is x equals 0. Let's get into the habit of writing it into the picture. There we go. We can fit it all in. 1, 0. Okay. And then the point 2, 1. So 2, 1 is right there. And we said it's an increase. So the other one was 1/2 and -1. And just like that, look, we're already done drawing this graph. Now remember, it doesn't come back down. It's not like a parabola. It does keep going to the right forever, and it keeps going up forever. So it's never going to actually come back down. So it is always increasing. So now, one of the first things I like to fill out here is the asymptote. See, when I look at the asymptote, and don't forget I'm put a V for vertical asymptote, we already said it's x equals 0. And the reason I want to bring this up is, see, it says x. So anything you talk about up here that deals with an x will be affected by the 0. 0 is going to show up somewhere, starting with domain. See, domain, we usually ask, does the graph go to the left forever? Well, no, it doesn't. There is a cutoff on the x, and it's 0. So then I mentioned the x, I mentioned the 0, and notice how my graph is to the right of the 0, meaning the x's are getting bigger and bigger, so x is greater. All right, so there you go. We are now to the right of 0. No, you don't have to leave class yet. Just let's keep this thing going. But again, it is to the right of the x, so it goes into positive infinity. Remember another way of writing that, of course, you could say it goes from 0 to infinity if you want to use interval notation instead. Remember, we use a parentheses because it is an asymptote. We don't actually make contact. Now, my range, when we were doing exponential functions, my range was the one that always had issues. But now look, does this graph go down forever? Absolutely. Does it go up forever? Yeah, very slowly, but it goes up. So my range is all real numbers. And remember, we have different variations of saying all real numbers. We'll go through all of them as we do this. All right, and now they've switched it on me. Look at this. Because your range is all real numbers, it says your y's are going up forever. Your y's are going down forever. So let's talk about the y's going up, getting greater and greater. Well, as your y's go up, it does go to the right side forever. So as x goes to infinity, there was no cutoff on the right side when it was going up. So don't forget, this is how you know where to look. They're saying when your graph goes up, that's on this side. Well, it's also going to the right forever. When your graph is heading down, y is going to negative infinity. Are your x's? Well, no, look, your x's are being cut off. So remember how we said that 0, as soon as you write it, it was going to show up in 3 places. My domain, and now it's going to be in one of these. Well, there it is. There's the 0. As your x's go to 0, because you can't go negative infinity, they are dropping forever and ever is what we're saying. And then the last thing is, what's the x-intercept? Well, we see it right here. It's also right there in our table we created earlier. Remember, we have an x-intercept, not a y-intercept this time. And the x-intercept is 1, 0. All right, so there it is for the first time, one of our parent functions. Now, let's try the next one. All right, so we are drawing a log. This is a parent function because there is no adding or subtracting. The b is 1 over 3. So because the b is less than 1, this will be a decrease. So I will see a drop happening. Now, it is a parent function. So one of the things that I can do right away is draw the asymptote. The parent function always has x equals 0 as the vertical asymptote. So there's my vertical asymptote. In fact, let me put a v here for vertical, and there it is, x equals 0. So we already know 0 is going to have an effect on these, right? On 2 of these things. Anything with an x, of course. All right, well, let's go with our table now. So we know our b value. So according to what we mentioned earlier, there's my x and my y. Automatic 1, 0, there's my x-intercept, which, of course, I can also name over here already and draw it. So you see, just taking care of 3 things as I go. The other one we said is your base, which is 1 over 3, and always the number 1. So now you see, this is why we know this is a decrease, because this was 1, 0, but I'm going 1 over 3, 1. See, I'm very close to that asymptote there, which is why we said there is technically another point, 1 over b, which means flip it. If I'm going to flip this over, that's just a 3, and then my answer would be negative 1. Remember, it just means flip the b. Flip the base is what we're saying. And so this one does help me out a little bit more. See, it's 3, 1, 2, 3, negative 1. And there it is. This is why we see that decrease. And so remember, we're coming right off of the wall here. Let me try this out. And then it just slowly keeps dropping and dropping forever and ever. Remember, it doesn't get horizontal all of a sudden. No, it keeps dropping. It goes it goes right forever and down forever at the same time. And then over here, it just kind of keeps climbing up, but it never goes past the 0. So looking at our domain, well, again, our domain is going to be affected by the asymptote. There's a cutoff. So my domain would be from, there's my x, there's my 0. And because I'm on the right side, you might say, but it's dropping. It doesn't matter. I'm on the right side. My x's are still greater, or from 0 to infinity. My range, on the other hand, goes down forever. Absolutely. Look at that. It does drop forever, and it goes up forever. So my range is all real numbers. Remember, we do have what we call the double R that represents all real numbers. So yet again, another variation of it. And then behavior. Now remember, it's asking, as your y's go greater than go to infinity. So they're asking as your y's go up. Well, as you go up, notice it doesn't go to the left forever. It keeps getting closer and closer to zero. So that's where this zero that we mentioned in the vertical asymptote is going to come up this time. Because as your y's go up, right, your y values get greater, you're getting closer to zero. But as your y's head down, negative infinity, so they're saying as you head down, well, your graph is going to the right forever. So if you're going to the right forever, then that's where positive infinity comes in. So again, those are the only things you have to be careful with that end behavior. Everything else is pretty standard. All right. Well, let's keep it going. Have a few more graphs here to go just to practice. Let's see if they're going to start moving things on you. Oh, there it is. They're finally going to start moving things on us. But just remember, we're still going to use our rules when it comes to transformations, moving things up, down, left, right. So remember, you've been working on that all year. But if you need a little help, of course, you have your word wall as well. And so graphing logarithms is what we're doing right now. Notice they're still calling it growth and decay. It's increase and decrease should be the real term there. But look, when your h is inside the parentheses, aka stuck inside the log, well, that's when you go left and right. But remember, we always think opposite for those. And of course, when you have a number outside the log, not stuck in there like the h, that's when you move up and down. So these are the things that haven't changed. There's the domain, as we've mentioned. It's x, and then whatever your h is, your range is always all real numbers for the graphs of logarithms. So with that said, here we go. I'm going to start off with the parent function. So the parent function is y equals log base 4 of x. Remember, the parent function does not include any extra numbers. No, the 4 is a base. That's not considered an extra number. The -1, that's the extra number. That is not part of the parent. So I'm going to start off with my parent points. There's my x, there's my y. Let's see, these numbers are nice. Look at the b values of 4. So we already know it's automatically, just like we said on the other side, 1, 0. That's for sure. And of course, the base, which is 4, and then 1. Now, remember, we are going to make a move here. So right now, I'm just going to draw it in pencil because I might have to erase it, of course. There's my original asymptote. There's the point 1, 0, and the point 1, 2, 3, 4, 1. All right. Our base is a 4, so we will have an increase, but we see that here already. So my graph is kind of doing this right now. And yes, don't forget, it does keep going up forever, very slowly, but it does go up. And then it heads down here. All right, but now we have to talk about this move. Now, when we were doing exponentials, we said if you move up or down, then the asymptote will also move. So if the asymptote is right here and I move up, see, it's still in the same place. If I move down, still in the same place. But if I move left and right, this asymptote is going to be brand new to us. And so looking here, we have a number that's inside of a parentheses, which means I'm going to be going, got to think opposite. I'm going to go to the right 1 space. And if I'm going to go to the right just 1 space, then that means I have a brand new vertical asymptote. Remember, you're going to the right. So even this line is going to move. And that new horizontal asymptote is x equals, well, it's got to be +1 because if you're at 0, here is the brand new vertical asymptote. You're going right through the number 1. So x equals 1 is our brand new asymptote. Let's write that in over here, x equals 1. But now I'm ready to just move everything over 1 space to the right. So this point, 1 space to the right. This point is 1 space to the right. And just like that, there we go, getting closer and closer to the asymptote. And then climbing very slowly, but climbing. Let me exaggerate that point, miss it just by a little. But there it is. You could barely make the difference between the original and then this one. All right, but don't forget what we mentioned. You have a brand new vertical asymptote. So this number 1 is going to show up twice. We already know it's going to affect the domain, and it's going to affect one of the end behaviors, not both, just one. So your graph does not exist on the left side. So then I'm going to say x, here's the number 1, but because I'm to the right of it, my x is greater than 1. Or you could say from 1 to positive infinity. My range, well, the range, if you notice the pattern, it is not changing. The graph goes down forever, goes up forever. So we can say all real numbers. And remember, this is the third way of saying all real numbers using interval notation, of course. And behavior. Now, we know the number 1 is going to show up on one of these. So f, remember, y goes to infinity means as your y's go up. So it's going up here. So when it goes up, it is going to the right forever. So if you're going to the right forever, that's the infinity. Here it says my y's are going to negative infinity. So that means heading down. So when my y's head down, notice I don't get past the number 1, but I get very close to it. So that's where the number 1 is going to come in. Again, as soon as you get your vertical asymptote, we know that number is going to show up 2 more times. Now, the last thing it does say is give me the x-intercept. We do have a new one. It's right at the number 2, so it is 2, 0. All right, so there we go. Now, the other thing you could do is, obviously, if you're moving your x's to the right, you could always add a 1 to these values to the table. All right. Now, look at number 4. Number 4 says f of x is equal to the log base 3 of x minus 2. Look at the big difference, though. When it comes to the parent, this is the parent function. What is new to this problem? The minus 2. But there is a big difference here. For this problem, the number 1 was inside of a parentheses. This is not inside of a parentheses, which means this is not left or right. As soon as I see this minus 2, and it's not in a parentheses, then I know I'm going to head down 2 spaces. And when you're moving down, remember earlier, because I moved to the right, I had a brand new vertical asymptote. But if my original asymptote is here, all right, let me move this up now. If my original asymptote is here and I move it down, well, notice it didn't really go anywhere. It's still the same spot. So I will tell myself there is no new vertical asymptote. So I'm going to stick to the OG. There is no new one. All right, well, if there's no new one, I can already start drawing this part here. At least there's no new horizontal asymptote, vertical, sorry. So I'm going to write that in already because there's no new one. All right, let's talk about the parent now. So for the parent function, it does say log base 3 of x. So the b is equal to 3. So that's going to be an increase. So we know it's going to look like this. If you give yourself an advance, tell yourself in advance what it's going to look like. It makes it easier. All right, here we go. X, y. It's always 1, 0. That's the great thing about a parent function. Those numbers are never going to change. 1, 0. And then, of course, the base, which is 3, and then 1. All right, so 1, 0. 1, 2, 3, 1. Now remember, this is the parent. This is not our final answer. So I wish these graphs were a little bigger so that they wouldn't get jumbled up so much. But there we go. There's the parent. And now remember what we have to do to these 2 points, because we're not going to have a new vertical asymptote. It's staying. I'm just going to move everything down 2 spaces. So here I go. Moving it down 2. 1, 2. 1, 2. There we go. All right, I'm ready for my domain. Now remember, my vertical asymptote, I like starting there, is x equals 0. So I know 0 is going to show up in the end behavior and in the domain because it says x. It's affecting the x's. So there's the x, there's the 0. Again, we are to the right side of that asymptote, so x is greater. My range, well, we said that's never going to change. It's all real numbers. Remember, I'm going to show you the three versions of writing it, all real numbers there for short. All right, remember, y's are going to infinity. This is the one that talks about up. Then this one's the one that talks about down. So when it goes up, notice it's going to the right forever. So they're talking about this end behavior. Well, it's going to the right forever. So this is the infinity. But when you head down, they want you to look at this side. Well, notice it doesn't go to the left forever. It's only getting closer to x equals 0. And that's where the 0 comes in. Remember, the vertical asymptote will have an effect on two other things. Now, the x-intercept is the one that's a little tougher here because remember, when you're trying to find an x-intercept, remember, you got to make your y equal to 0 there. So I need to try to find it here. Now, looking at my picture, I can't tell. So I'm going to do a little bit of work here. For my x-intercept, we already know, here's my equation. The y is equal to 0, log base 3 of x minus 2. So I'm going to add the 2 over. See how that goes there. 2 is equal to log base 3 of x. And this is why we like to do the circle method. This is the technique. See, if I turn this back to an exponential, I start at the base, go to the other side of the equals, and then I come back. Look at what we just have here. It's going to say 3 to the power of 2 is equal to x. Well, 3 to the power of 2 is 9. So then that's my x-intercept. So I was way off in my picture. Look at that. 1, 2, 3, 4, 5, 6, 7, 8, 9. I should have been touching over here, but all right, close enough, we'll say. But you can definitely find your x-intercept with the skills that we've learned. All right, 2 more to go. Let's see how these go, because now we're going to have 2 transformations that we're going to do. So let's look at the parent first. The parent is the base and the x, with the word log, of course. We have 2 other numbers that are going to affect it. We have a number 9, big number coming our way, and the number 4. All right, so first of all, the 4 is not on the inside, so that's going to be up 4. The 9 is on the inside, so I have to think opposite, and in this case, I'm going left, 9 spaces, but remember, you are going left, so because of that, we're going to have a brand new vertical asymptote, and that brand new vertical asymptote is going to be x equals -9. Don't forget we said left. So of course my number is going to be a negative. Let me go write that in over here. Vertical asymptote, x equals -9. Remember, I don't need to draw this. I already know by saying left 9. All right, but let's talk about the parent now, because that's where the graphs always begin. So here we go. X, there's my y. All right, 1, 0, always. Base, 1 over 2, and then the number 1. Now remember, this one is a little strange, so I do like to bring in that third one. Don't forget, this answer will automatically be -1, and then all I have to do is flip it over. Remember, this is the base, and whenever needed, we can flip it and get our 2 over 2 and -1. All right, remember, we are just drawing the parent right now. So 1, 0, 1/2 1, and then 2, -1. So there is the parent function, just to get us going. But now I'm just going to move everything. So my new asymptote is -9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's -9. There is the brand new asymptote. Remember, my graph has to get closer and closer to it. So x equals -9. All right, let's count very carefully here. I'm moving everything up 4, left 9. So left 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And up 4, 1, 2, 3, 4. There's my first one. And of course, this one here, this is a lot easier to work with. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 1, 2, 3, 4. See, once you notice where your points are located, they're literally diagonally go one away, kind of thinking it that way. Then we can draw it already. And then it drops, 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 and it goes up, 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 up. All right, looks like we're going to need a little work for that x-intercept. They do want me to find it, but we'll get to it shortly here. All right, so domain. All right, when we're looking at our domain, let's see what we get here. We know the -9 is going to show up, so there's the x, there's the -9. I am still to the left of this line. You see, you can't worry about this. Here's my line. I'm either to the left or to the right of it. So I'm still to the right. Sorry, I said left earlier. I'm to the right of it. So then my x's are still getting greater than -9. My range, well, we already said it's all real numbers. That's not changing. So there's my double R for all real. And behavior, y goes to infinity, that's up. This is down. All right, let's talk about up. But when it goes up, notice that's when I'm getting close to touching this x. So that's where the -9 comes in, which means when it heads down, it is going to the right forever. So then we say infinity. Now the x-intercept, again, another very interesting one to try to figure out here. So let's see how that one goes. My x-intercept, let's see. 0 is equal to log of 1/2 x plus 9 plus 4. Okay, a lot of things happening there on that one. All right, well, the first thing I have to do is move the 9 over. Sorry, the 4 over to the other side. So move the 4 over. So 4, -4 is equal to log base 1/2 of x plus 9. All right, I'm going to rewrite it as an exponential. So that's 1/2 to the power of -4 is equal to x plus 9. And I'm kind of out of space here. So let's see, maybe I'll go this way. 1/2 to the power of -4. Well, the negative power is bringing the 2 up. And then 2 to the power of 4 is just 16. So I get 16 is equal to x plus 9. And then when you subtract the 9, all right, so 7. 7-0 again. The great thing about knowing how to write something back as an exponential. All right. Questions or concerns? X-intercept, don't worry too much about it. As long as you know how to draw, you should be okay. All right, that brings us to the very last problem. So for the very last one, let's see. The +1, up 1. The -2 is right 2, which means we have a new vertical asymptote, and you're going to the right so that it's x equals 2. All right, we've got a new one. So I could go write it over here, vertical asymptote, x equals +2. All right, let's talk parent now. The parent is y is equal to log base 5 of x. So your base is 5. This is going to be an increase, so it's going to go like that. All right, here come my two usual. 1, 0, 5, 1. Again, once you know these 2 points, easiest ones for the parent. 1, 0, 1, 2, 3, 4, 5, 1. Okay, so there's the parent. All right, let's make the moves. So first move, we have a new vertical asymptote at 2. So there it is, nice and big, nice and visible. Give it some color. X equals 2. All right, we're going up 1, right 2. Up 1, right 2. Up 1, right 2. And just like that, we get our graph of this log. Remember, domain says my asymptote is a 2, and I am to the right of it. So then once again, x is greater than 2. My range is all real numbers, so I'll go classic negative infinity to infinity. This one says the y's go up. Well, when my y's go up, I'm going to the right, so that's infinity. When my y's go down, well, here it is going down, but I'm getting close to x equals 2, so that's why we put a 2 there. And then the only concern here is the x-intercept, which from the looks of it, it's somewhere between 2 and 3, so I know it's got to be 2 point something, comma 0. So all I have to do is find that. But again, it takes some work to do that. Don't stress yourself over the x-intercept too much today, at least for this part. But let's see if we can work it out. X-intercept, 0 is equal to log base 5 of x minus 2 plus 1. So let me subtract the 1. Negative 1 is equal to log base 5 of x minus 2. I'm going to rewrite it. So then it's 5 to the negative 1 is equal to x minus 2. Going to add a 2. So you're still going to need the calculator for this one because notice 5 to the negative 1 is like saying 1 over 5 plus 2. So I guess you could say 2 and a fifth is equal to x, which if you use a calculator, that's about 2.2. But again, don't stress so much on the x-intercept today. We can get to that. Usually, I think in the next section, we're going to work more on solving these that way. All right. So there you go. Drawing logarithms, we're still using left, right, up, down. But remember, in the parentheses, right and left, not in a parentheses, up and down. So just keep that in mind on whatever your vertical asymptote is. Remember, that's what kind of starts setting everything else off. So I would do that first. All right, everybody. Next thing you'll do is work on the classwork for today. So get started on that for a few minutes and have a good day.